Chapter 2 was motion in one dimension. Simplest example of kinematics. And Chapter 3 is motion in two dimensions. And the chapter has several sections. There's a trigonometry review. There's a section on vectors. There's velocity and acceleration in two dimensions. And then there are two sections on examples: projectile motion and uniform circular motion. Now, why stop at two dimensions? After all, we live in three dimensions. How do we describe kinematics in two and three dimensions? Remember, the word kinematics means the description of motion by mathematical methods. And the kind of mathematical objects we need to use are vectors and coordinates and functions. Now, vectors are very important in more than one dimension because in two or three dimensions there are different directions. And positions, velocities, accelerations, those are all vectors. They depend on direction. Think of a race car moving around a circular racetrack. Its direction of its velocity is constantly changing. It's always tangent to the racetrack. As it goes around the track, it's changing in position. Now, of course, we live in three dimensions, but in fact, many three-dimensional problems reduce down to two dimensions. And in elementary physics, two-dimensional motion, motion on a plane, is common. But we rarely deal with truly three-dimensional motion. So Chapter 2 will be limited to motion in two dimensions. Motion on a plane. There will be axes, let's say x and y axes. And the particle will be moving around in this plane. So its x coordinate will be changing, its y coordinate will be changing. Now, where's the vector? Well, we set up a coordinate system with some fixed point. That's called the origin. And the vector, the arrow from the origin to the particle, moving object, that is the position. That's the position vector. Now, you have to get used to the notation. Whenever we write a vector, we put an arrow over the symbol. So x with an arrow over it stands for this vector. X with no arrow over it stands for the x coordinate. And you know they're different between x with a vector symbol and x without the vector symbol. You see, x with the vector symbol has a direction. And the second coordinate, y, will be the projection of that vector onto the y-axis. So one way to represent a vector is by giving two components: a component in the x direction and a component in the y direction. And we'll sometimes use that notation for vectors. We also have unit vectors, so we'll call I the unit vector in the x direction, and j will be the unit vector in the y direction. So another way to represent the vector would be to say it's x I hat plus y j hat. You know, it's the number x, well, it'll be a number with a unit, some number of meters, let's say, times a unit vector which points in the direction of x, plus a different number, y, times the unit vector in the y direction. So we could write the vector in this form, or we could just write it as a list of the x coordinate and the y coordinate. We use both of these notations. I mentioned that we live in 3 dimensions, but many mechanics problems reduce down to 2 dimensions. So here's some examples of that. Planetary orbits. The planets revolve around the sun, including the Earth. So here's sort of an artist's rendition of the solar system, not drawn to scale, obviously. Now, the solar system is in 3 dimensions, but it turns out any planetary orbit will be on an orbit plane. All the orbit planes are about the same. So, you know, the orbit plane of Jupiter is pretty much the same plane as the orbit plane of Earth. So, you know, we have these, well, in principle, the orbit planes could be different, but for each planet, there's a plane that the planet moves on, called the orbit plane. Though the solar system is 3-dimensional, the motion of a planet is really only 2-dimensional. That's because angular momentum is constant. And we'll come back to talk about angular momentum later in the semester, but since the angular momentum vector is a vector perpendicular to the orbit plane, and since it's constant, well, that means the orbit plane never changes. So the Earth just continues revolving around the sun on a 2-dimensional plane. An example where the motion is really 3-dimensional would be a charged particle, like an electron, moving in a magnetic field. It turns out that most generally the orbit or the trajectory of the particle will be a helix. And so that's something really 3-dimensional. But that's not for Physics 231. We'll talk about magnetic forces and motion in a magnetic field in Physics 232. All right, so vectors and coordinates for 2-dimensional motion. We have a particle which is moving around on a 2-dimensional plane. So here's a particle. It's moving around on this green plane. Now I can set up a coordinate system, 2 coordinate axes, 2 perpendicular axes, x and y, that span the 2-dimensional plane. And I'll have 2 coordinates. The coordinate on the x-axis is the projection of the position vector down onto the x-axis. So that'll be x. The projection onto the y-axis gives me the coordinate y. The projection of this vector r. R is the position vector. It's the vector from the origin that I set up the coordinate system to the particle. So the position of a particle is a vector, r, and I can write it in terms of Cartesian coordinates as xi hat plus yj hat. I hat is in the direction of the x-axis, so there's I hat. J hat is in the direction of the y-axis, so there's j hat. And now you should read the book to review vectors. If I take xi hat plus yj hat, I get r. That's how you add vectors. You take the first vector, then you take the second vector, put the tail of the second vector on the head of the first vector, and then the sum is the tail of the first vector to the head of the second vector. So I have x I hat plus y j hat is equal to r. So study section 2, which is called scalars and vectors. What's a vector? A vector is a mathematical quantity that has both direction and magnitude. So let's take, for example, this position vector r. That's the displacement of the particle from the origin. The magnitude of r, which I write as r vector between two vertical lines, or sometimes that's just called r with no arrow over it. By Pythagorean theorem, that's x squared plus y squared square root. It's just the distance from the origin. But you see it has the x component in one direction, the y component in a perpendicular direction. So I have here a little right triangle. And the hypotenuse is the square root of x squared plus y squared. That's the length of the vector, or that's the distance from the origin. Now you have to make sure you're using the vector notation correctly. If I write A, that's not a vector. If I write A with an arrow over it, that's a vector. If you don't include the arrow, you don't know what you're doing. If I write A, and there's also a vector, then A probably means the magnitude of the vector A. So here I have r with components x and y. R without the vector symbol just means the length of r, or the magnitude of r. It's the square root of x squared plus y squared. So in general, I can always expand any vector into the Cartesian direction. I can write A vector is ax I hat plus ay j hat. You notice I don't put a vector symbol over ax because ax is not a vector. Ax is just a number, possibly with a unit. Ax times I hat, that's a vector. Ay times j hat, that's a perpendicular vector. When I add them together, I get the vector A. So ax and ay are the projections of A onto the x and y axes. Often you'll have to add vectors. Geometrically, you add vectors by saying A plus B. Oops. Let me just set B in some other direction. This is the direction of B. A plus B is this vector. So geometrically, if I have vector A, put an arrow over it so I remind myself it's a vector, and I have vector B, which will have a magnitude and a direction, then this is the vector A plus B. But that's geometrically. If you have to calculate a vector algebraically, then it's just a matter of adding the components. So the x component of A plus B is AX plus BX. And the y component of A plus B is AY plus BY. Well, anyway, you'll be using these math techniques throughout the semester. So read section 3.2 carefully. You should have your notebook with you when you're reading the textbook, and you should be taking notes. Make about a page of notes for each chapter. So spend about an hour on section 3.2. Now, some people have taken physics in high school. You may have already mastered vectors in high school, but if you haven't already mastered vectors in high school or in an algebra class, spend about an hour reading section 3.2 and taking notes. Well, I showed before position vector. There's some fixed origin in space, And the arrow from that origin to the position of the particle is called the position vector. Now what about the velocity of the particle? Well, that's just like motion in one dimension. The velocity is the rate of change of the position. Now, position is a vector, so velocity will also be a vector. It won't be in the same direction as the position vector. It'll be in some direction. In terms of equations, the velocity vector, and I indicate that it's a vector by putting an arrow over the symbol, is the rate of change of the position vector, r. So let's suppose I have the origin here. The particle is here. So there's the particle. R is this vector. So this is the vector r. And I could project that onto, x and y axes. There are the x and y axes. But there's some origin, and I measure the displacement from the origin defines the position of the particle. Now the particle's moving around in this plane, so the position changes in time. So that's a vector, and it's a function of time t. Now, what's the velocity? Well, let me put the velocity in a different color. Let's say the particle is moving off this direction. The velocity vector could be that vector. Particle maybe is moving in that direction. Let's put on a little curve which indicates the motion of the particle. Let's say it started down here, it's moving up here, it's moving over here, then it's moving over here. Well, let's not make it quite such a drastic acceleration. Let's just say that it's moving like that. The velocity vector is tangent to the trajectory curve. Maybe I can write this better. The velocity vector would be this direction. Well, let's put it in pink again. The velocity vector, when the position is here, would be tangent to the curve. So I guess it would be off in this direction. That's the velocity vector. The velocity doesn't have to be in the same direction as the position relative to the origin. We'll be considering circular motion where the velocity is perpendicular to the position. So you have to not confuse the direction of the position with the direction of the velocity. So the velocity is the change in r divided by the change in t. Delta r over delta t. The change in r is r at t plus delta t minus r at t. It's the initial position of r at time t. It's the final position of r minus the initial position. That's the change in position. So it's r at t plus delta t minus r at t, divided by the time over which that change occurs, delta t. Now, if delta t is a large number, then we call this the average velocity. But if delta t is a very small number, then this is the instantaneous velocity, instantaneously at the time t. Now remember, r is x I hat plus y j hat, where x and y are the coordinates. Now x and y will be changing in time, but I and j do not change in time. I mean, I set up this coordinate system with y in one direction and x in another direction, and I never change that. But the coordinates for the position of the particle will be changing. So those will depend on time. So the change in r will be the change in x times I hat plus the change in y times j hat. And to get the velocity, I divide by the change in time. dx dt is vx. dy dt is vy. So this is the component of velocity in the x direction, the component of velocity in the y direction. Or I could use that other notation and call this vector vx comma vy. It depends on what notation is most convenient. Now for constant velocity, I have a simple equation. I can just say r at time t is some r0, that's the initial position vector, plus vt. Remember, for one dimension, x at time t is x0 plus vt. Well, only if v is constant. So if I'm assuming v is constant, then there'll be an x component v0x, and a y component v0y. Y of t will be y0 plus v0y times t. So these are the equations we're used to for one dimension. But now we have two dimensions. But you see, I just sew together each dimension to get the two-dimensional vector. These equations are only true for constant velocity. And we're more interested in accelerations. So don't use this equation unless you're absolutely sure that the velocity is constant. Now, what about acceleration? Well, again, it's just like in one dimension. The acceleration is the rate of change of the velocity, just like in one dimension. Only velocity is a vector. It has different directions. So the rate of change of that vector will have different directions. It'll be a vector. So acceleration is another vector. And just as we had the relation between v and r over here, we'll have a similar relation between a and v over here. The acceleration is the rate of change of the velocity. It's the velocity at t plus delta t minus the velocity at t. I'm here combining two vectors, so that's a vector, divided by delta t. Or in terms of components, it's delta vx dt times I hat plus delta vy dt times j hat. Those are the two components of a vector, ax I hat plus ay j hat. So you see ax is the rate of change of vx. Ay is the rate of change of vy. So again, if we have two dimensions, the Cartesian coordinates satisfy the same kind of equations as we had for one-dimensional motion last week. But now I have to sew those two together to get the full vector. And in particular, in the case of constant acceleration, the velocity is v0, some initial velocity vector, plus at. So at time t equals 0, v is equal to v0, because this term is 0. But at a later time, v will be v0, that initial velocity, plus the acceleration vector times the time. It'll have the direction of the acceleration vector. It'll have a magnitude which is increased by the factor of t, the time. And for the position as a function of time, we have an equation exactly analogous to the equation for one dimension. R at times t is r0, initial position vector, plus v0t, v0 there is the initial velocity vector, plus 1/2 at squared. So the acceleration gives a term in the position proportional to the square of the time, just as in one dimension. So you can write these equations for the vectors or for the vector components. So for example, x at time t is x0 plus v0x times t plus 1/2 ax times t squared. Now, those equations are only true for constant acceleration. We'll consider an example of constant acceleration in a minute, but we'll also consider an example where the acceleration is not constant. If the Cartesian coordinates are separable, that is to say, if ax does not depend on y and ay does not depend on x, then the two-dimensional problem just reduces down to two separate one-dimensional problems. We have constant acceleration in the x direction and constant acceleration in the y direction. Or more generally, if the acceleration in the x direction does not depend on y, and the acceleration in the y direction does not depend on x, which would be true for constant acceleration, we could separate the x-coordinate motion and the y-coordinate motion. So instead of solving a two-dimensional problem, we would solve two one-dimensional problems and then sew them together. An example with separable coordinates is projectile motion. At least if you're ignoring friction. A projectile moving through the atmosphere has friction with the air, a kind of aerodynamic force called air resistance. Now that may not be separable, but if we neglect air resistance, then we just have a constant acceleration, and any problem with constant acceleration is separable. So we can just solve the two components separately and then combine them. We reduce the two-dimensional problem to two one-dimensional problems. On the other hand, an example which is not separable is circular motion. Now there's a separate section in chapter 3 on projectile motion and on circular motion. And you will need the results from those two chapters for the homework. Section 4 is projectile motion. So here's a picture of a projectile. An object moving in Earth's gravity near the surface of the Earth. So if you're not too far from if you're near the surface of the Earth, these equations will be very accurate. If you're far from the Earth, then you have to use Newton's theory of gravitation. But if you're near the surface of the Earth, you can just use the fact that there's a constant acceleration, g, directed downward. So we'll set up a coordinate system. X is a horizontal coordinate. Y is the vertical coordinate. And we'll have some object, could be, for example, a golf ball, which is, well, a golf ball is subject to some air resistance, so maybe we should better say, I don't know, a soccer ball. It'll be moving in some direction horizontally, and it'll be moving vertically, up and down. So maybe the soccer player kicks the ball at this point. It will go off down the soccer field. Meanwhile, rising, it will reach some maximum height. It'll continue going off in the same direction down the soccer field, and it'll land some point on the surface of the Earth. So we need a coordinate in the y direction to describe the vertical position, And we need a coordinate in the x direction to describe the horizontal coordinate. Now, what's the acceleration of a soccer ball moving near the surface of the Earth? It's g. No, it's a vector. It's AY. J hat. It's a vector. So the acceleration of the soccer ball is, let's write it this way, AX in the x direction, comma, AY in the y direction, there is no acceleration horizontally, neglecting air resistance, so the horizontal acceleration is 0. There is an acceleration in the y direction. It's minus g. And g is the same for a golf ball or a soccer ball or a football or anything. A hammer, a cannonball. G is 9.81 meters per second squared. We studied the acceleration in Earth's gravity back in chapter 2. So AX is 0. So the x motion, the horizontal motion, is just constant velocity. So x at time t will be x0 plus v0x times t. That's an example of constant velocity. But for the vertical motion, y of t is y0 plus v0y times t plus 1/2 ay times t squared. Ay is minus g, so it's minus 1/2 gt squared. There are two equations you need to write down in your notebook. Now let's work out an example problem. Let's take the example of a golf ball as a projectile. And let's calculate the position where it hits the ground. Actually, a golf ball is affected by air resistance to some extent, but we could say that's small, or we could say playing golf on the moon where there's no air, so there's no air resistance. We wouldn't have 9.81 meters per second squared because the acceleration on the surface of the moon is less than 9.81 meters per second squared, but we'd have some corresponding value. Now, when you hit a golf ball, the initial position is x0 equals 0 and y0 equals 0. You know, a golf ball starts on the tee. It's a ground height. We could take that to be the coordinate y equals 0. There's an initial velocity. v0x is v0 cosine theta, and v0y is v0 sine theta. v0 is the initial speed, the speed of the golf ball as it leaves the tee. Theta is the angle that the golf ball leaves the tee. It's the angle relative to horizontal. So I guess, let's put it in a different color. This would be theta, that angle. So if you hit the golf ball at a 45-degree angle, it's traveling up with the speed over the square root of 2 for the x component of velocity, and also the speed divided by the square root of 2 times the y component of velocity. Cosine of 45 and sine of 45 are both 1 over the square root of 2. And just to put in a number, let's say the initial speed is 13.4 meters per second, approximately 30 miles per hour. So this isn't Tiger Woods hitting a golf ball. he hits the golf ball with a much larger initial speed. This is maybe Tiger Woods when he was 6 years old hitting a golf ball. Let's say the initial angle is 785 radians. That is 45 degrees. And that's measured above the horizontal. And we want to know how far did it go. We want to know how far did the golf ball go before it hit the ground. So we have to have some way of specifying where does it hit the ground. Well, from the picture it's obvious. It hits the ground where y is equal to 0. So when we say where it hits the ground, in other words, at y equals 0. So let's set y equals 0. V0y is V0 sine theta times t minus 1/2 gt squared is equal to 0. Now that's an equation I can solve for t. So t is 2 V0 sine theta divided by g. And I gave a value for V0 and I gave a value for theta. So that turns out to be 1.93 seconds. But that's not what I'm interested in. What I'm interested in is this distance. But I have an equation for the horizontal distance. It's x0 plus V0x times t. So I would just say the horizontal distance is x at time t. It's not V0t. It's V0 cosine theta times t. It's x0 is 0, so it's V0x times t. V0x is V0 cosine theta. I guess I have this wrong, so this calculation is probably wrong. It should be V0 cosine theta is 1 over the square root of 2. T, I figured out from the condition that it hits the ground, is 1.93 seconds. So this number is probably wrong. It's V0, it's 13.4 multiplied by 1.93 divided by the square root of 2, which is 1.414. So, this is about 2. This is about 13. So 13 times 2 would be 26. That's this answer, but that answer is wrong. It's 36 divided by 1.4. Well, 1.4 is roughly 1.5, so divide by 3, multiply by 2. So it's 26 divided by 3, call that 9, multiply by 2, that's 18. So it's about 18. And the unit is meters. It didn't go very far. This was a relatively small initial speed. You'll have a lot of problems like this to work out in the long kappa assignment. So, projectile motion. Here's figure 3.17 from the textbook, showing a projectile following a parabolic trajectory. Study this and read about it in section 4 of chapter 3. Now, the final section in chapter 3 is circular motion. Here is the summary of section 3.5 at the end of chapter 3 on uniform circular motion. I don't really have time in the video here to go over this in much detail, but you'll have to be reading that section anyway. In uniform circular motion, the speed is constant and the velocity is tangent to the circle. So this is called uniform circular motion. It's a special case where the speed is constant. Now the velocity is a vector. So the velocity is a vector. The magnitude of the vector is the speed. The direction of the vector is the direction of motion. So let's suppose we have a little object here, a little mass m, going around a circle which has some radius, I don't know, let's call the radius r. You could think of a race car going around a circular track with a constant speed. I suppose the race car is going around the track 60 miles an hour. Or you could think of this as a satellite revolving around the Earth, a satellite in orbit around the Earth on a circular path, on a circular orbit. Or you could think of this as the Earth revolving around the sun. You can think of this, here's the sun, and here's, well, let's not just say some mass, let's say this is the Earth. The Earth revolves around the sun every 365.25 days. It travels around the sun. Now, what's the acceleration? Well, here's where things get interesting. The velocity is tangent to the circle. Well, that's pretty obvious, because the change in position will just be in the direction of the velocity. The velocity is the rate of change of position. But now we want to know, what's the rate of change of velocity? Well, if I waited a little while, the particle would be here. The velocity is always tangent to the circle, so the velocity would be that way. So let's see what's the change in the velocity. At this point, we'll call that 1. At 1, we have a velocity in this direction. So that's velocity 1. Now at this later point, we'll call that 2, we have the velocity in this direction. So that's the velocity at time 2. Well, I really should indicate this is a vector, and this is another vector. Now, what's the change in velocity? What's v2 minus v1? The change in velocity is this velocity, is this direction. So that's delta v. v2 minus v1. Here's v1, it's this vector. Here's v2, it's this vector. Here's delta v. It's v2 minus v1. So if I go out v2 and then I come back minus v1, I get this direction. Now, suppose the time here is very small. Well, then this vector will be pointing back towards the center of the circle. So if I take a very small time interval, then v1 will be in this direction, v2 will be in this direction, and delta v will be back towards the center. And that's called the centripetal acceleration. And that's shown here in the picture as this vector directed towards the center of the circle. And so the direction is towards the center of the circle. And that's called centripetal. Centripetal is a Latin word meaning directed towards the center. It's a fancy word for directed towards the center. So here's the velocity. It's tangent to the circle. Here's the acceleration. It's towards the center of the circle. This is a case where the velocity and the acceleration are perpendicular. Directed toward the center of the circle. Now, what's the magnitude? Well, that was first explained by the Dutch scientist Huygens. Huygens lived at the same time as Newton. If it weren't for Isaac Newton, Huygens would have been the most famous scientist of his day. But he couldn't be the most famous scientist of his day because that was Newton. But he lived at the same time as Newton. He had some disagreements with Newton. He had some remarkable discoveries in science about the theory of light. Newton also had a theory of light. But in any case, he was a mathematician, and he proved the formula for centripetal acceleration is v squared divided by r. Newton also used this result. I don't know if Newton got the result by reading Huygens' paper or if he figured it out himself. But anyway, the acceleration is v squared over r, directed towards the center. And that's called centripetal acceleration. There's also a relation between the speed and the period and the radius of the circle. The speed is 2 pi r over t. 2 pi r is the distance around the circle. So 2 pi r is the circumference of the circle. So if t is the time it takes to go around the circle, then the speed, which is constant in uniform circular motion, is the total distance over the total time. The total distance is the circumference. The time is the period of revolution. So for example, we know the distance from the sun to the earth. It's 150 million kilometers. We know the period of revolution of the earth around the sun. It's 365.25 days. So we could calculate the circumference, divide by 1 year, and we'd have the speed of the earth as it travels around the sun. How fast is the earth moving in its orbit revolving around the sun? And then what's the corresponding centripetal acceleration? Newton did this calculation, and then he applied his theory of gravity to relate the centripetal acceleration to the mass of the sun and the mass of the earth. By Newton's second law, acceleration is force divided by mass. Well, you'll have to read this section 3.5. There will be some problems on the Lon Kappa assignment involving uniform circular motion. And you will have questions on this subject on the next exam as well. So you should be taking notes so that you'll be able to make a sheet of equations that you can use during the exam. All right, so that's an introduction. This video has been an introduction to Chapter 3, but it's not a replacement for actually reading the chapter. It's only an introduction. But now that you know what Chapter 3 is about, you can go read chapter 3 and learn a little more deeply what it is. And then do the homework problems.